Hello everyone, our project is the Digital Companion for Obesity, sponsored by Novo Nordisk. We would like to start off by thanking our technical directors, John, Fola, Anubhav, Karthik, and Shabana for their enormous support during this project. We have a 5-person team consisting of 2 computer engineering majors, Afalabi Abiyomi and Yashaswini Mandalam, a double major in computer and electrical engineering, Justin Watkins, as well as 2 electrical engineering majors in Dela Olivo and myself, Connor Vincent. Founded in Denmark in 1923, Novo Nordisk has a long history in the treatment of diabetes as one of the first companies to produce insulin. Today, they are involved in the research and development for the treatment of chronic illnesses. These illnesses include obesity, diabetes, Alzheimer's, and sickle cell disease. They are currently well known for their diabetes drug Ozempic and weight loss drug Wegovy. Today, obesity is a worldwide epidemic affecting 41.9% of Americans and 39% of people worldwide. There are few treatment tools that specifically target the behavioral and psychological aspects of obesity. Depression, social isolation, and several comorbidities affect people with obesity at very high rates. Our team developed a method for helping people experiencing these issues. Our team's anticipated best outcome was to create an iOS application, compact hardware design with health sensors, a machine learning model to take in user data, and overall provide a personalized and seamless system. Our team accomplished our anticipated best outcome. We created an iOS application that connected a user to health-related information. We designed and developed several different iterations of custom hardware that would collect health data on a person. Machine learning models were developed to personally target and assist someone struggling with obesity. These tools together produced a personalized and seamless experience with a user. Our team's technical accomplishments included an activity recognition model, stress detection model, data pipeline, front-end design, health sensor research and testing, adaptable testing hardware, and a foundational training for large life contextual description model. Personally, I worked on the health smartwatch, which is the hardware-based part of this project. Specifically, I worked on the prototype hardware design of the board schematics and PCB layout, which also included the assembly of the prototypes. I also worked on the research and selection of various health sensors and the testing of these sensors. The health sensors that were found to be important included heart rate and heart rate variability, electromyography, electrocardiogram, electrodermal activity, and temperature. These are 2 of the prototypes the team designed, a Revision 3 hardware which was ordered and assembled, as well as our Revision 4 hardware which was planned and designed but was not able to be manufactured. This next revision would be continued and assembled in the future development of this project. Now we will move to our next designer, Yashaswini Mandalam.
I primarily worked on the machine learning portion of our project and also a little bit of the embedded systems. With machine learning, the primary goal is to get our sensor data, put it through trained models, and get a useful health prediction about our user. Currently, we have 3 trained models: activity recognition, stress regression, and emotion recognition. The activity recognition model uses the inertial movement unit, or IMU sensor, to predict what activity someone is doing. For our project, we were primarily focused on identifying eating activity. We were able to improve the eating activity prediction of our model from last semester by replacing it with a CNN LSTM model. To make our eating prediction even better for the future of this project, we foresee using video data to capture eating movements to learn the pattern of someone's eating behavior, and eventually, when the model is better trained with the supplemental video data, we can remove the video monitoring so it doesn't feel like an invasion of privacy for our user. Next, we have our stress regression model, which takes in data from the EDA, heart rate, and temperature sensors as input and outputs a numerical value indicating how stressed someone might be. A value of 0 to 0.4 is low stress, 0.4 to 0.7 is medium stress, and anything greater than 0.7 is considered high stress. This model was trained on a data set collected by MIT, where the test subjects performed different activities and rated their perceived stress levels. Since this model is trained on subjective data, we foresee future teams testing and tuning this model with more data to make sure that it's personalized for each user and is outputting the accurate stress levels. Third, we have our emotion recognition model, which takes in 30 seconds of audio data as input, and as output, it can predict the emotion in the voice. These emotions include neutral, happy, sad, angry, fearful, disgusted, and surprised. This model was trained on a huge data set made specifically for the task of emotion recognition with AI. Picking up someone's audio data might seem invasive, but since our project was a proof of concept, we had the freedom to make models like these without worrying about the restrictions of a market-viable product. Both the activity recognition and stress regression models are currently deployed on the Amazon AWS environment, and my team member Afolabi will be going more over the Amazon AWS and cloud aspect of our project.
I was assigned the task of working on the cloud aspect of the project. I was assigned the task of working on researching and implementing a possible deployable database for storing and processing all video, audio, text, and health sensor data received from the phone app and also from the watch. Utilizing AWS proved the best cloud deployment option for cost management and minimization, also for efficient machine learning model training and processing. The idea behind my choice of platform is to utilize Firebase integration with the Flutter app, also to send information to AWS and back to the phone app, for efficient development of working data pipeline for user interactions, whereby user information from sensors and user entry on the phone app are sent to AWS for machine learning model processing and training. The messages are sent back to the user app for encouraging a healthier lifestyle and helping them do without the obese behaviors and habits that they normally have. This is a further breakdown of the idea behind the cloud database, whereby it can be integrated in the further future, whereby video, audio, text, and sensor data can be collected and stored for processing and also for training the machine learning models. And though it wasn't fully integrated in the back end, we were able to achieve the anticipated best outcome for cloud development, for storage, and also for Flutterfy connections and the other AWS implementations. Coming up next will be the next designer, Dale Olivio, who will be going over the further breakdown of the app development.
As one of the electrical engineers in our team, I was involved in both hardware and application development. My task included working on hardware revisions 1 through 3 and managing the front-end development of our app. Initially, we began coding in Swift, but later switched to using the Flutter framework due to its simplicity and its capability to develop cross-platform applications for both Android and iOS. Despite the learning curve, working with Flutter was still a lot easier and versatile, and our development speed improved considerably. So displayed here is the app's dashboard and home screen, which is organized into 3 main sections: eating tracker, mental health, and physical health. On the left, you'll notice a hardware graph mockup. Since my primary responsibility was the front end, I focused on designing the user interface and integrating placeholders for the eventual inclusion of real user data. The data currently shown is mockup data, which serves to demonstrate how the app will eventually look and to showcase its potential functionality. Here we can see a real example of using mockup data and replacing it with real-time data. The graph is dynamically putting data points related to user stress regression from our backend system and displaying it in real time. This integration was achieved with the support of AWS in our backend, enabling users to view their stress levels live within the app. Our next designer, Justin, will discuss backend development and machine learning.
Hi, my name is Justin Watkins, and I ended up working on a lot of different aspects for the project, from everything from the DynamoDB and GraphQL APIs, along with Kinesis data streams for the back end with AWS, Flutter state management systems and Bluetooth packages, same thing with the embedded system and sensor data processing for things like heart rate variability. But in general, the one thing that I do want to end up describing here is the work on the large life contextual description model. Now, what we ended ended up trying to end going into this semester with is a way to be able to tokenize health sensor data. And this was approached by another group also that created something called the 1LLM multimodal large language model. And what they wanted to do was create a universal framework that they can embed different types of data into the projection and project it into the embedding space that a large language model could understand. So the way that they ended up doing this is creating this type of architecture, which we just expanded upon. And the way that these tokenizers were done is by simple 1D or 2D convolutional neural networks that could end up interfacing with this universal encoder. So that's all we ended up having to do in order to simplify the health sensor data tokenization. And we could end up putting it into this universal encoder in order to try and end up training all of these projection experts and the entire model in its entirety in order to be able to create a proper large language model embedding for this physiological sensor data. So the way that we ended up doing that was getting a bunch of different health data sets. And there's plenty of them around the internet, but they weren't annotated with anything too in-depth or too insightful in the sense of like behavioral cognitive change or something that like a therapist would end up describing the state of a person. And that's essentially what we wanted. And while that wasn't possible, as a proof of concept, these data sets were probably fine with what we ended up producing. And the idea here is that we ended up utilizing something called PVS Gen. And it's a universal synthetic data sensor data generator. And what it does is it can take any type of empirical data that you have a sample of, and then it can end up producing more and more data for that in a synthetic manner that will still follow the same trends and overall statistical properties of that data set. And the reason why this was useful is because we could come across any type of sensor data that we ended up having, seeing a data set for it, and then it would end up being able to produce it based on that data set that it we ended up finding. But we also ended up utilizing web scrapers in order to be able to get a large intervention text corpus created. And the way that we ended up utilizing that was trying to shift the large language model parameters more towards this physiological sensor data space and being able to describe what was going on with a user in these types of terms so that it could kind of correspond into this type of training sequence we were trying to end up getting, where we took that health sensor data. We also ended up intermittently training it with video data of user actions to ensure that no catastrophic forgetting occurred, and at the same time to ensure that we could also get a good handle on user actions and external events that were happening to them, while at the same time we could describe these internal states that were going on based off the health sensor data itself. And then from there, the idea is that we were able to create, with some fine tuning of the large language model, intervention prompts themselves, where based on some set of health sensor data, we were able to create an intervention prompt that could be associated with it. So as a proof of concept, this was useful, but we definitely think that there's a lot more need for data to be generated. And in general, this whole system is a way to be able to perpetuate that need, where we can create an auto-annotated pipeline by taking in more video data, by taking in more health sensor data, and by taking in potentially different sensors and annotating it with semantic feature extraction library. And we can really create a useful product here in the future based off of the concepts that we've been able to prove in this portion of things. So we definitely want to be able to thank our technical directors from Novo Nordisk, John Canavari, Fola, Anubhav, Kartik, Shabana, and especially Professor Sunak, Mike Smith, Brendan, all of you guys, and thank you so much for the presentation today.